to the universe. What does it say there? So question 5 says, in the diagram, the graphs of F and G are drawn. So there's F here, there's G there. And then it says the F is this equation, G is this equation. X is an element of, X is basically between 0 and 360 degrees. And then it says A, who is A? A is this point over here. It is a point of intersection of the graphs. Okay, perfect. And then it says, what does it now say? So before we even read the question, oh yeah, well, the questions are going to ask us to ask whatever questions I was about to ask right now. But it says here we need to get the values of A and B. So A is this value here, and then B is this value there. So from what you know so far, what do we know without like knowing the specific values of A and B? Like looking at where A is, what does this value tell us? And what does this value tell us?
Wait, I told you that I haven't gone through it, so I don't know.
Oh, okay. Sorry, madam. Sorry. So sorry. So let's see. What does it say? Okay, yeah. So since you haven't learned it yet, it's fine. We'll just go through it. So with all trigonometric graphs, the big idea is this is the format that you actually want to remember, right? It is y. Let me just do this. Let's see here. Y is equal to A, and then a trig graph. I mean a trig expression, and then bx minus p plus q. This is the format of a trigonometric graph, right? So with A, B, P, and Q, they mean something specific. So for and this is the same for like all the graphs, right? For all sine, cosine, tan graphs. The only thing is for A, right? A represents the amplitude, of which the amplitude has a formula. It is equal to the maximum y value minus the minimum y value. Let me write it in a way that will be easy to understand. You see, maximum y minus the minimum y, like this, over 2. This will always be the amplitude, of which that's what you always need to do to get amplitude, or sometimes your sketch will always give you the amplitude. For example, if you look at this graph of G, the amplitude, you can see the highest value our graph goes to is like a 1. The lowest is like a -1. So you can see that the amplitude here is going to be 1 minus -1 over 2, which is going to be 2 over 2, which is a 1. You see, so you can see the amplitude will always be the distance between a point of rest to the maximum and then back to a point of rest. And it does not necessarily need to be a 0, you see, because if your graph was like somewhere up here, a point of rest just refers to you know, 1 point going back to where it started, and then again that same iteration. So this here would still be an amplitude of 1 over there. Do you see?
Yes.
Yeah. So that being said, that's what A is. A is always the amplitude. So for a coarse graph, though, the idea is the same. You see, for you not to get confused, you can always just use your formula. The maximum value here is a 4. The minimum is a -4. So for the coarse graph, the amplitude there would have been like a 4 minus -4. 4 minus, this is going to be like 8 over 2, which is like a 4. Perfect. So that's what A does. A is just the amplitude, of which if you look nicely, you know, the distance between here and there, that's just 4 units. But then the formula helps for cases where your graph was like moved and stuff. So if you had maybe a picture of a coarse graph that looks like this, the amplitude, you would just say, okay, this is the lowest value, this is the highest value. So you'd say -1 minus -4, And then here your amplitude would be -1 plus 4. And then here you'd have 3/2 as the amplitude, you see. So that's what A is. A is always the amplitude. Now the thing is with the graph of a 10 graph, A is not necessarily an amplitude, because remember a 10 graph, you can imagine, I mean, it's just lines, you know, so it does not necessarily have like an amplitude. So your value of A in a 10 graph, let me put here y is equal to A 10x. Let me just put it like this. You can't necessarily say amplitude, right? Because there's no amplitude here. So this is not amplitude. Okay. So what A does is it just gives you an idea of like the steepness of these lines, if I can put it that way, because the higher the A value, the steeper these curves will be, you see. So not amplitude, let's just say here indicates steepness, steepness of curves, you know, slash gradient. No, steepness of curves, of which steepness is referring to gradient anyways. So that's fine, you know. Let me just make an arrow here, gradient, you know, slope, whatever you want to use to remember. So that's what A does. So B, I'll have to just write this somewhere else now. So with the equation that we wrote out, A sine B, you can see is just a placeholder for the number that will be directly next to X. It's just a placeholder for a number that's directly next to X, you see. So this number here that's directly next to X, we refer to it as frequency, you see. Now frequency also has a formula. It is 360 divided by the period, you see. Now these two words, we have to state what they mean and what they refer to. So frequency tells you, so obviously for a 10 graph, this number is 270, you see. So let me write here 410. This is 180. And let me just explain what this means. Frequency refers to how many complete graphs in a space of 360 degrees or 180 degrees, if it's a 10 graph. So for 360, this would be a sine or a cos graph. And then for 180, this would be a 10 graph, you see. So frequency just tells you how many complete graphs you have in a space of 360 or in a space of 180. So what I mean by that is the standard images that we know of trig graphs, we usually just see them from 0 to 360. But let me just draw an image that goes from -360 to +360 of a sine graph. That image may look something like, oh, yo, I'm flopping here. Do this, ish, and this. On this side, it would look like this, and then this. So this is what you would see in a sine graph from 0 to 360. If it's standard, this number would be a +1, this number would be a -1. The equation of this graph would be sine x, you know, y is equal to sine x. Now, if you look nicely here, the number in front of the sine there is just a 1, and we can see it, the amplitude there is a 1. The number in front of the x here is also just a 1. It's telling us that there is one complete graph in a space of 360 degrees. The 360 degrees does not have to be starting from 0. It doesn't matter. It could start anywhere, but as long as after 360 degrees, you are seeing a full picture, it means your frequency is 1. Frequency is just how many complete graphs you have in a space of 360 or 180. So that's why with a 10 graph, the image looks like this. Let me just also show it from -360 to +360. So -360 will be like somewhere here. 360 will be like somewhere there. Our standard asymptotes, we see them at let me do 180 in the middle here so that I don't like mess up. So asymptotes will be like at 270 and at 90. Here it will be like negative 90 and negative 270. So as long as we know that, right, we'll have like an asymptote here and an asymptote there. Now asymptotes actually split up complete 10 graphs. That's one thing we always need to remember. So in between all these 10 graphs, I mean, in between all these asymptotes, we're gonna be seeing full graphs. So that's why a 10 graph is actually full. This is just half a 10 graph. This is also half a 10 graph. Now this is a full 10 graph. You see, between here and here, it's actually 180 degrees. So for a 10 graph, if your frequency is 1, it means in a space of 180 degrees, you'll see one full graph. That's why here between 90 and 270, you'll see a full graph like that. And then you'll see like a portion like here because the other portion would like extend here. On the left, you would still see these curves here, and then here you'd still there. So you can see with the 10 graph, it's just these squiggly lines going on and on forever and ever and ever, you see. So the equation of this graph would simply be y is equal to 10x. You would have a 1 there because there's one graph in a space of 300 and, I mean, in a space of 180 degrees. For a cos and a sine graph, there's one graph in a space of 360. It means the one number there will be a 1. If that number was a 2, if you had, let's say, y is equal to sine 2x, you would have two graphs in a space of 360. So between 0 and 360, halfway along the x-axis, you would see a full graph already. And then the other 180 degrees, you'd see like another full graph, you see. So meaning on the left side here, you would also have the same image, right? Where you would see like one full graph in 180 degrees and then another full graph going on and on and on and on and on. You see, so this here would be 180 degrees. This would be like negative 180 degrees if this number was a 2. Do you see it?
Yes.
Perfect. So while we're still on this formula, you see that it says frequency is equal to 360 divided by the period. That's because the frequency and the period, they are more like yin and yang. You know, they just work together. You know, where there's period, there's always a frequency. So period and frequency, the definition of period in this case, it's just going to be how long it takes to get a complete graph. It takes to get a complete graph. You see, so in these images, they are easier for us to use to give an idea of the period. So because there's one full graph in a space of 360, you can see, you can just ask yourself, how long does it take to get a full picture? It's just taking 360 degrees. And remember, a full picture just refers to one wavelength, which is basically from one point on the graph and then to a point where that motion is repeating. You see, so if you're from here to here, that's a full graph. Because here you're going down in this way, going up, and then you're going down again, you see. So you can see from here to there, that's one full motion. So you can already see this is like negative 1. Yep.
So you see, since you said from those points it's a full graph, right? My question is, why don't you start from, let's say, why don't you make, you see where you say at point 0, right? And then to the end of that other one at 360, right? At the point, why don't you say that's a full graph? Where do you begin your full graph?
That's the thing. It doesn't matter where you begin. It's all a matter of a full wavelength. You know, if I start here, for me to have a full graph, it will need to be me going back to a point where I'm doing this. You see, so if you see here, I'm going up, right? And then I go down and then I'm still moving. Then I'm here now. The moment I'm about to do the same thing again, that's a full graph. You see, and you can see it's all working together. It's still just 360 degrees from here to there. The same way, it's still also just 360 degrees from here to there. So this is to also highlight that it doesn't matter where you start. Even if I started back here, you can see if I go up, down, and then here, the moment I'm about to go up again, you see, I'm about to repeat this exact same motion. So the moment you're about to repeat the exact same motion, that's how you know you have a full graph.
Okay.
So, yeah. So with the 10 graph, it's also the same, because if I have a graph like this, if I have a picture like this, right, and I see this motion from 0 to 360, a standard image looks like this, right? There will be 360 here. Now going forward, you would see the same image again. You see, this would be like at 200 and at 720. You see, so that's a full picture where you are doing the exact same thing again. So we know that here, that's a full image. The moment this whole image is about to repeat, you will have another graph there. So that's how you know that the period here is equal to 360 degrees, because the period is how long it takes to get a complete graph. It takes you 360 degrees to get a complete graph. For an image like this one, it takes you 180 degrees to get a complete graph. You see, because in a space of 180 degrees, you have a full graph. So the period is 180, but the frequency is 2, because you have 2 graphs in a space of 360, and it takes you 180 degrees to get one full graph.
Oh,
fantastic. So that's period and frequency. Same formula. They sort of work together. So with P and Q, it's all about shifts along the x-axis or the y-axis. So with all that we've been saying here, right now we are at P and Q. So let's start with P. So P is just a horizontal shift. You see, it's a shift from left to right. You see, so if it's a plus P, it means you're shifting to the left. If it's a minus number there, it means you're shifting to the right. You see, so an example of that is the thing with tree graphs is it's usually easier to explain these things, right, when they are close to the origin, because you will just need to compare it to a standard picture. So we say this is what a standard sine graph looks like, right? Let's just draw it quickly here. A standard sine graph looks like this from 0 to 360. On the left, it looks like that from 0 to negative 360. So the idea is this is just y is equal to sine x, you see. So what you want to actually see here is that firstly, there's a 1 here that's invisible. And then there is a 1 here that is also invisible. And then there's like a 0 there that we don't write. And then there's like a 0 there that we don't write. So this is to show you that, okay, yes, this graph has an amplitude of 1. It has a frequency of 1. It has not been moved to the left or to the right compared to the standard one. And it has not been moved up or down. That's how it looks like this. But the moment you want to move it to the left or to the right, let's say you now have, let me make note of certain key values you can use to double check what has happened to a graph. So you see here, there's 0, 180, and 360. Up here, we know that the x value is like a 90. Down here, which is a turning point, we know that the x value there is like a 270. So this is like all these key information, right, for us to identify a normal standard sine image. So in a situation where your graph was moved around, let's say it was moved 30 degrees to the left. So if it was moved 30 degrees to the left, instead of passing here at 0, it would be passing somewhere there at negative 30. Instead of turning here at 90, it would be passing somewhere here at like 60. Instead of cutting the x-axis at 180, it would be cutting somewhere at like 150 maybe. Instead of like turning at 270, it would be turning somewhere at 240. And then instead of having a full graph at 360, we would have a full graph at 330, somewhere there, you see. Oops, 30. So your image, I mean, you still have the same image, right? It would still go up, but we said at 60, it needs to turn somewhere. And then at 240, it needs to turn somewhere. So then it cuts the x-axis there, cuts the x-axis there, cuts the x-axis there. So our image would look something like this. You see, it's the same picture, but then these key values here, they're different now, because this is to show that this image was moved 30 degrees to the left. So it would still carry on with the same shape, going on and on and on. However, what is important is to take note of how, if you're focusing on one portion of the image, you can see how the standard image has been affected. So the equation of a graph like this would look something like y. So if this is like a positive one up here, negative one up here, this equation would look something like y is equal to sine x plus 30. Because remember we said if it's a positive number, it has moved to the left. So from a standard image here, the image was moved 30 degrees to the left. So a plus 30 is what shows that.
Okay, maybe
You see.
pause for like 2 seconds. I just want to write that part quickly down.
Which one?
The bottom part. I just want to quickly sketch it.
Oh yeah, you can sketch the thing. Let me just pause this. Fantastic. Did you say you wrote down everything? You wrote it down. Yeah, we're good to go.
Yes, I just need to like sketch the graph quickly.
Oh yeah, take your time. Take your time. But with what we were saying now, right? That's what the horizontal shift affects. So with the p, which is this variable there, right? With the value of p, so here we have here y is equal to let's go back to what we were saying, a blah blah blah, and then here plus p, I mean q. So q is a vertical shift. Vertical shift, meaning it's a shift from top to bottom, you see. So with the vertical shift, it's almost self-explanatory. But then the thing is, a vertical shift does not affect your amplitude. It just affects which numbers you use to get your amplitude. So meaning if you have a sine graph like this, right? And you are required to do what? What are you required to do? If you have what's this thing? If I have, let me just draw this nicely. Yo. There we go. So this is a Cartesian plane. If you have a standard sine graph, as we have mentioned, we're just doing a sine graph just for the vibes, because it's all the same for all the graphs really. So if this is y is equal to sine x, I mean, again, we know 0 to 360, it looks like this. So if you have another graph somewhere, if you carry on going on, you'll just have multiple graphs going on and on and on and on and on. It really doesn't matter. The point I'm trying to stress here is that don't think too much about how a graph is only from here to there. No, a graph goes on, a tree graph goes on forever, to the left and to the right. So this here would be like negative 360. Yeah, it doesn't matter. So if this graph was moved 1 unit upwards, right? Let me just take this image here. Oh, sorry. Oopsie. Take this image here, copy, and then let me paste it here. So if this image, right, was moved 1 unit upwards, let's just try and see what that would look like if it was moved 1 unit up. Oh, but we were flowing. Come on now. Hey, yeah, ne? So if this image was moved 1 unit upwards, this is what it would look like. So if this whole thing was moved 1 unit upwards, right? It's not very nice to look at, but this is what we could expect. You see, everything would be touching the x-axis now at some point. Let me just do this, do this, like that. You see, so remember from this original picture, right? We know that our graph would be going from 1 to like -1. So if you move the whole thing upwards, it's now going to be going from +2 to 0. Do you see? Are you still there? Connection. Oh, wait. Maybe I'm muted. Oh, mic is gone. Mic is back.
But I think cut, or was it the other side? It cut it.
Cut it. So, anyways, wait, what's the last thing you heard?
You were saying if you vertically shifted and you were busy saying, "Oh, it's not pretty to look at."
Yeah, it's not, doesn't look very smooth, right? But the idea is originally it's going to 1 and -1, right? This is the equation. Amplitude is just the 1. If you move it 1 unit upwards, it's going to go from -1 to it's going to go from 0 to 2 now. You see, because it has been moved 1 unit upwards. Yeah. So the equation of this graph would be, hey, well, what's this thing now? Hi, man, interruptions. So the equation of this graph would be like y is equal to sine x plus 1, like that. Excuse me. Because this is to show that the graph was moved 1 unit upward. Everything else is still the same. Amplitude is still a 1. Frequency is still a 1. It still has not been shifted to the left or the right. So we can imagine with all this that we've said, when a standard graph has undergone a lot of changes, we can expect, a different kind of a picture based on what our numbers for P, Q, A, and B are. So an example of that is, say we have a random equation. Let's say y is equal to 2 sine, let's say half x. And then here, let's say minus 60, and then minus 1.
Wait,
let's just
give me a
go and see
moment.
what this
I want to quickly go and get my calculator.
Yep, you can do that. You can, what you call, we're working on an example. So if you now have, let's say, all this happening, right? It's just a matter of now visualizing it based on a standard image. As long as you can remember what the standard image looks like, drawing other graphs is not always going to be a mission. So let me just, you see here, I'm putting this down here because up here I want to again just write out a standard sine graph and then put its image. So if it was a standard one, sine is equal to sine x, y is equal to sine x. Let's just visualize what we would have seen from 0 to 360. From 0 to 360, we would have just seen a picture like this, you see. So this is what we know. Halfway we would have x-intercept, and then at 90 would have a turning point, and then at 270 would also have a turning point. Let's see, there we go. And then at -1 there. This is what we would see if this was the equation. This one now, first let's deal with the half side of things, where I wrote a half in front of the x there. So that's quite important. So this is saying in a space of 360, you have half a graph. You see, because remember with frequency, it means the same thing all the time. The number in front here tells us how many complete graphs you're going to see in a space of 360. You see, that's what we wrote here. How many complete graphs in a space of 360? That's if it's a cos graph or a sine graph. So if you're going to see a half a graph in a space of 360, or rather, let's maybe do that on its own first before we like use the complicated version of things. Let me maybe do this one for later. Let me do this. Let's maybe do that one as the next one, because we're just going to cement, some simple concepts here. So if you have something like sine and then a half x, all this means is in a space of 360, you're going to have half a graph. You see, meaning 360 degrees again, you have another half of a graph. So meaning in a space of 720 degrees, that's where you have a full sine graph. See, like that. So with our image here, let's maybe keep things, let's maybe just change this to a 2, because using a half is that's just being extra for nothing. But let's just make a frequency a 2. So in a space of 360, we're going to be seeing 2 graphs. So the image that we would be seeing on our Cartesian plane what we need to be careful of is we have to accommodate everything, you see. The shift. So you may be asking, but where do you start? What do you draw first? What point do you put first on your graph? The first thing you can always do for yourself is, okay, you just want to visualize what a normal image would look like from 0 to 360, right? And then make the changes from there. So firstly, you would see, okay, wait a minute, I have two of them in a space of 360. So automatically where 180 is, you want to acknowledge that X value. Automatically what you know is in a space of 180 degrees, you would have two graphs, right? And then you can move to this. You usually want to start from the inside and then now accommodate the numbers outside here. So here you can see, okay, frequency is a two, so you can already put something like this for yourself. And then here you can see, okay, a graph was moved 60 degrees to the right. So if your image was moved 60 degrees to the right, now you need to take into account these specific X numbers and then move all of them 60 degrees to the right. So what you want to do, what you would do for yourself is, okay, fine. We know that from your graph would be cutting the axis at 0, right? But then because it's moved to the right 60 degrees, it's not going to cut the x-axis at 0 anymore. It's going to cut it at 60. You see, so somewhere at 60, you would make a point. Or let me remove this for now because we might run out of space. So somewhere at 60, you are going to have your graph passing the x-axis. So let's just put a 60 over there. Now what we know is between 0 and 90, 90 is where your graph usually turns. So in our case, instead of it like turning at 90, because the frequency is at 2, it means that the whole thing is shrunk in half, you see. So instead of like cutting after 90, instead of like turning after 90 degrees, it would then only be turning after 45 degrees. So meaning from 60, 45 degrees later, that would be somewhere at 105. Yeah, somewhere at 105, that's where it's going to turn. And then 45 degrees later, it would then be somewhere at like 150. So you know that this is where it's going to have another special moment. And then 45 degrees later, which would be like at 190. Why am I even doing it so small? Let me not worry about the scale right now. Let me make it a bit bigger because I don't know why I'm making these tiny dots here. Let me just make them big because we don't have to draw multiple graphs. So I mentioned 60 here is a specific point, and then 45 degrees later, that's also a special value we need to take into account. And then 45 degrees again later, that's going to accommodate this value. And then 45 degrees later, that's going to accommodate this. And then 45 degrees later, that's going to accommodate this value there. So let's see. 45 added to this, that's going to be like 200 and 240. 240. Yeah, 240. Yeah. So what we already know is between 60 here and 240, you can already see that's 180 degrees, meaning we know we are going to see a full graph between that space. So instead of us now drawing a picture that looks like, oh my God, good Lord, dismiss, yes, like, so instead of us seeing a picture that would look like this, we would need to take into account the amplitude and the vertical shift of 1 unit upwards. So instead of us looking at something like this only, we would need to think to ourselves, okay, fine, the image does look like this. However, it is moved 1 unit downwards. So instead of us seeing something specifically like this, we would be seeing, let me just delete it. We know that it would be somewhere a bit lower. Now, instead of it just being, so it would be somewhere at like -1 here, right? Where our graph would be starting its whole up-down motion. So what we need to keep in mind is let's put -1 here, let's put +1 there, let's put +2 there, and then let's put -2 here, let's put -3 here. So the big idea here is, let's see, we know that this graph, now we can have some sense of direction. We know it's gonna, instead of it starting at 0, right, the graph was moved 1 unit downwards. So it would start somewhere here. The amplitude is telling us it would go 2 units upwards. So from -1, going 2 units upwards before it turns, it means that it's going to go all the way until like 1, right? And then it's going to come down, and then it's going to be in line with this. And then it's going to need to go 2 units downwards again. So it's going to go 2 units downwards again until it's somewhere there. And then it's going to go up 2 units again, you see. So in a space of 60 to 240, you can see that's 180 degrees, you see. And then what you can also see is this graph has an amplitude of 2, and you can see that it was definitely moved 1 unit downwards, and it was moved 60 degrees to the right. And this 2 is telling us that it would take, you would see 2 graphs in a space of 360, but then if your value of frequency is a 2 here, your period will come out as 180. So this is what you would see in this small image here. Obviously, going to the left and to the right, you would just see the same image, you know. Here you would still see an image like this, and then, you know, it would still just go on forever. To the right side, you would still also just see an image like that, and then it will still also just go on forever. I just focused on this small portion because this small portion, it's easy for us to relate it to a standard image. You know, you moved it down, you increased the amplitude, you shrunk it. This is just showing that this is what's important, you know, these values here, so that you can see, okay, wait, it's going to turn there, it's going to come back here, it's going to turn there, and then it's going to come back there. So that's the big idea with trigonometric graphs and these 4 values there.
Oh, okay.
Yeah. The last, nice. The last thing to mention is if this number is a negative or a positive, you know. So if that number is a positive or a negative, it does not, if you have, let's say, -2 sine x, the amplitude is still a 2, because amplitude is all about distance, and distance cannot be a negative. So the idea also is you want to remember, if it's a negative here, it means that instead of your graph starting off by going upwards, it would start off by going downwards. You see, meaning it would go down to like -2 here, and then it would go up to +2 there. Cool. Perfect. So that is the main idea behind this kind of work. So you can see it's quite a mouthful, right? Meaning it's not the kind of thing where you look at it once and it's like, everything is in your brain. It's more like you look at it and then you start working with it bit by bit. Cool. Fantastic.